Okay, everyone, welcome to our continuing physics seminar series. Of course, this semester it's all virtual and online, which has allowed us to bring in some really great people from far away who we've always wanted to have, but we never were able to get all the time for them to come and travel here for a couple days. Slava Turinsky I'm probably mispronouncing the last name very badly, is our speaker today from JPL. He got his degree from Moscow State University, where he was also assistant and associate professors. And now he's a staff scientist and a leader, a group leader at JPL for NASA. And he's going to be talking to us today on the aspect of a gravitational lens imaging of exoplanets.
Excellent, Nick. Thank you very much. And it is nice to be in Wichita finally. So at some point, I'd like to visit your university and meet everybody here. So it would be very nice. But given the situation, I think it's for me it's a pleasure to be here and talk with you about the project that we've been involved for the last at least maybe 5 years. And so the main question about are we alone in the universe, and do we have expectation that beyond Earth there will be some life forms? I usually ask that question in the audience and asking, is there a life beyond Earth atmosphere? And people raise hands up or down, and so some people believe, or some not. But that was, of course, a trick question. So there is life beyond Earth's atmosphere. So this is the space station, and we have people orbiting Earth regularly. We have quite a few people have flown around our planet and visiting the moon. Soon, hopefully, we'll have another set of people who would be working on the moon. But the reality is there a life beyond the Earth at sort of the Earth orbit? And so here we will be talking about our project that is funded by NIAC. We are going through phase 3 project, and this is a direct multi-pixel imaging and spectroscopy of exoplanets with a mission to the focal region of the solar gravitational lens. And this mission is motivated by the fact that the multiple exoplanetary discoveries happened during the last 20 years. And at some point, we do expect that will be those planets identified, those that harbor life. And the main question, can we see those planets? Because we used to see images, multi-pixel images of multiple objects, but can we see those objects which are very far from us? The closest object is 3 light years away from us. So the Proxima b, but most of the stars that have planets are way beyond the distance. So let me go through this project, through the discussion. Here I will be focusing on physics of the solar gravitational lensing. I will introduce what solar gravitational lensing is and why it has the advantages. Why do we need to study this very challenging optical lens, which is our sun? So can we use that lens to benefit really the exoplanetary research? And what does it offer, and what technology do we need to develop before we will be able to use it, or can we use it already? And so with this, let me bring your attention to the cradle of humanity, our civilization. This is our family portrait. So this is a solar system. There are multiple planets and satellites around those planets. And so we live around Earth, we live on Earth, and we hope to find life on one of those planets, but maybe not life the way we expected to see it, maybe microbial or bacterial life. There's some expectation we'll find some forms of life around Mars, then Ganymede, Enceladus, Europa. Those are the satellites of Jupiter and Saturn. But beyond that, can we see something? Can we see something else? And it looks like our challenge is really to look beyond the solar system and into the skies. This is the quick, sort of the fast history of the solar system exploration. See, we've been around every planet, many satellites. We've seen many of those objects. we deployed many spacecraft, and you see how many spacecraft we have developed. We've been there, we've done that. And so those objects where we expect to find life, as I mentioned, it's Mars, Europa, Ganymede, Callisto. So those objects, this is where we expect to see, maybe life on Europa, in the ocean of Europa, and Enceladus. So maybe some organic life there. So, but it is what it is. So basically, there is no way to see sort of life forms that we expect to be to see intelligent life. So we're looking for intelligent life, and we know that at times life on this planet may not be called intelligent even. So, but ultimately we try to find something that is that resembles us, and for that we will be looking beyond the solar system. Currently, by October 2020, we have identified many exoplanets orbiting nearby stars. We understand that those planets are formed around stars, and they're ubiquitous. So in around many stars, we'll find multiple planetary systems like TRAPPIST, for example. We have wonderful planets orbiting that star. There will be many more of those multiplanetary systems identified. By today, we have roughly 4,300 exoplanets confirmed. There are roughly 56 exoplanetary candidates, and only 3,200 of planetary systems where we know that there will be multiple planets orbiting those stars. Among those, we expect sort of 163 planets are terrestrial. So the meaning that they harbor planets with a solid surface and resemble, inner planets in the solar system. And so it's only a matter of time when we will identify Earth 2.0, the planet that orbits nearby star, and orbiting its star in sort of in a habitable zone where simply water can exist in 3 states. So so we expect that at those distances, the planets may have conditions where organic life may thrive. And so basically, with multiple spacecraft operating now and telescopes on the ground looking for exoplanets, we expect to identify those objects within the next maybe 5 to 10 years. And so hopefully then we will be able to do spectroscopy and confirm that those planetary objects, those planets that have atmosphere, and we can maybe study spectroscopy confirming the presence of the gases that we are looking for, methane, oxygen, nitrogen. And so those gases that actually indicate that there are some instabilities within the atmosphere, and instabilities actually related to living organisms. So it's a matter of not if there will be some discoveries, but it's a matter of when. And we have deployed a lot of resources now to identify those planets. So since 1998, where the first exoplanet was discovered, and Nobel Prize was given for that discovery last year. So we know that this area of exoplanet search is becoming a very significant area in astronomy. And so we expect that the planet, the Earth 2.0 will be identified soon. And so that is something that actually motivates research that we will be discussing today. So these are the nearby stars within 100 light years away from us. We have multiple targets to examine. There are quite a few exoplanets orbiting those nearby stars. Many more will be discovered because it's challenging to discover Earths around, the planets which are small compared to the. It will be it is very difficult to discover small planets around those stars. We are able to discover Jupiters, Saturns, the giants, but it's much harder to discover the small planets like Earth, Venus, Mars, because they're tiny in the orbit their stars. And so basically, at some point, once our technology will improve, we will be able to discover many more of those planets. But these are the nearby stars where basically this is our neighborhood, and we expect to see many of those planets to be discovered within the neighborhood. These are the telescopes that are being deployed already, that are operating in space. You see on the left, you see Hubble, Spitzer, Kepler. TESS is operational now. Soon we will have James Webb, and WFIRST will be launched. So these are the NASA satellites. At some point, we will, and this line indicates the presence of European research in space. starting with Koro, Gaia, Cheops, Plato. So the many spacecraft that orbiting Earth and with the objective of looking for exoplanets. There are also ground-based telescopes like Keck Observatory, a large binocular telescope interferometer. The many more telescopes are being constructed. And so essentially, those instruments will contribute to a very significant data set for us to look for, to work with the objective to discover planets that may harbor life. And so, but the biggest challenge for us is, of course, size. In this chart, you see in the middle, of course, this is our sun. And down to the bottom, you see a very tiny rock we call Earth. And so compared to Earth, compared to the sun, the Earth presence is very difficult to discover if you look outside the solar system, because it's a tiny object that does not emit light, it only reflects light. And so compared to its host star, in this case, the sun, the brightness of this object is extremely tiny. It's very small. And essentially, if you're talking about exoplanets orbiting nearby stars, in terms of brightnesses, I think they are representing objects which, sort of on the visual magnitude, there will be objects of anywhere between 32nd to maybe 38 stellar magnitudes. So those objects are very tiny, and discovering them with regular telescopes is very difficult. In this chart, you see a very nice selfie that Cassini spacecraft took of all us. So we are living down there on the planet Earth. And so Cassini trained its camera and looked back at Earth and took a wonderful selfie. And so, but that indicates that even a few astronomical units away from us, our Earth is already a very tiny object that is being resolved here with only like few pixels. And so, but if you go to very large distances, if you go to distances maybe 10 light years away, maybe 100 light years away, the challenge is really critical. So if you want to resolve, if you take our own Earth and put it at 100 light years away, so using classical instruments such as telescope and interferometer, we must have access to an aperture of 90 kilometers. So it's a large aperture, a large telescope we must have. And so to resolve that object with just one pixel, let me repeat, if I take our Earth and position it at a distance of 100 light years away from Earth, and to resolve that object with just one pixel, the telescope diameter must be at the level of 90 kilometers. So this is just 10 kilometers shy from the boundary of space. And so if you've been to Los Angeles, you see here Jet Propulsion Lab and Dana Point. So this is the size of the telescope you must have. And of course, this telescope cannot be operated from the ground because atmospheric distortions will be very significant. For that, you need to fly that instrument in space. And we just discussed that we were able to fly quite a few instruments in space, but the telescopes, the largest telescope that we are building now, which is only 6.5 meters, it is still on the ground. So we're talking about, of course, the James Webb telescope that is still being built. We're talking, but here again, it's a 1 pixel image. If you want to get multiple pixel images, you need to multiply that 90 kilometers by number of pixels you want to have. And so essentially, that actually tells us that going this path using classical instruments, it is infeasible. Let me put it softly. It is infeasible to develop instrument like that in space, because if we actually fly something like that, if it will be few angstroms thick, the telescope of that size, it will still weigh of trillion tons. And so even if you're able to deploy something like that around the sun, solar radiation pressure will remove that object from the solar system within 1 year. So even building and operating that instrument is impossible. So this is a challenge. And of course, we all get used to multiple images of our own planet with many pixels. So this is a blue marble image that was taken by NASA Terra satellite. And essentially it's a 10,000 by 10,000 pixels. So we would like to have, we are accustomed to see those objects, to have those high resolution photographs. Are we ever going to be able to have pictures of distant exoplanets with the quality like we used to? And this is the big challenge, of course. So because looking at the telescopes, again, I'm focusing on the telescopes. On the right, you see the picture of multiple telescopes that we were able to build. And here in the red circle indicates the European extremely large telescope that is being built in Chile, and whose diameter is 39 meters. So this telescope is showing on the left. And so it will get the first light around 2022, maybe 2023, given the COVID situation now. But this is what we can build on the ground. Somewhere here on this picture, you see James Webb telescope, which is 6.5 meter telescope. So basically, we can build very good telescopes. And last week, you had a nice presentation by Mario Paris from NASA headquarters, who was talking about progression in the telescope capabilities that we are able to have in the next few years. LUAR and HubX, these are the large telescopes that are being discussed, roughly 16 meters in diameter, maybe 22 meters in diameter. But remember, so these are the space telescopes which were launched. Kepler is operational. Hubble is, of course, also operational, but it's 2.4 meters telescope. James Webb will be 6.5 meter telescope. So again, I'm emphasizing 90 kilometers is the big aperture to have. And so there is no way to actually build it in space at the moment. So it's infeasible to do something like that. So, but this is why we want to talk about using the sun and using general theory of relativity to use the sun as a giant lens. Of course, the Einstein was the first one who suggested that the gravity actually bends light. The trajectory of photons that are passing by the sun are being bent towards the sun, and so this is the light gravitational deflection of light on the limb of the sun is roughly 1.75 arc seconds. And going away with the slightly larger impact parameters, the deflection of light will be a little bit less. And so this is the experiment, first ever test of general relativity conducted by Eddington. And it was a wonderful time when essentially the fundamental physics experiment can provide you with three possible answers. The first answer was deflection of light. The gravity is not of influence in the light travel. And so deflection will be zero. There were Newtonian arguments based on Newton's theory of gravitation. And so the deflection was 0.87 arc seconds on the solar limb. And of course, Einstein's deflection of light is 1.75 arc seconds. And we know this, so this is the telegram sent by Campbell, who was leading the expedition to Tahiti, suggesting that indeed general relativity was confirmed by the Eddington's expedition at a very good level. So since the Einstein was the first one actually who suggested that gravity can be used to influence the light trajectories of light. This is pages from his workbook, essentially in 1911, where he's deriving the gravitational lens equations. And so realistically, back then he suggested it will be very difficult to do anything with this type of predictions, because technology was not available at the time. Later on, we have seen multiple images of gravitational deflection. So now we know that microlensing events and gravity indeed affecting light propagation. So these are the pictures of a galaxy cluster Abell, essentially taken by a Hubble Space Telescope. You see those Einstein arcs, and essentially indicating that indeed gravitational deflection of light is happening not only around the sun, but around every massive body. And essentially, so that suggests that indeed this phenomenon is very well known. For the first time to discuss solar gravity in the context of a large telescope was given by von Eshelman. Von Eshelman, he was at that time professor at Stanford University, and he was the chief of radio science team on Voyager 1 spacecraft. And von Eshelman actually suggested that solar gravity may be used as a giant lens to amplify signals from extraterrestrials, from alien civilizations, radio signals that will be sent towards us. And we can use the sun to amplify signals that we receive from those from those civilizations, from those aliens. And back then he actually suggested that the solar gravity lens can be used for that purpose. Later on, we have done some work and shown that solar plasma that is surrounding the sun actually would prohibit using the solar gravity lens with the microwave frequencies, but using solar gravity lens with optical frequencies, pretty much it's those wavelengths, the optical wavelengths and infrared wavelengths will be pretty much unaffected by solar plasma. If you have a good coronagraph to block the sun, so potentially you can see the images of exoplanets or other sources which are amplified by the solar gravity. And here in this paper published by von Eshelman in '79, essentially he computes for the first time the maximum light amplification. And the sort of 2 pi kg, essentially, he is talking that the k would be the wave number of the observational wavelength, and g would be the Schwarzschild radius of the sun. So 3 kilometers. And if you use optical wavelength, you get this amplification of roughly 10 to the 11th. So that's a nice factor to have. So light amplification provided by the solar gravitational lens on the optical axis is 10 to the 11th. So this is a significant number that actually drawn a lot of attention to that solar gravity lens. That was our primary motivation to use that. Later on, we realized that once we use an optical telescope, we have to average that signal over the telescope aperture, and so the light amplification is quite less. It's not 10 to the 11th, and it's 10 to the 9th, but still quite nice. So where this phenomena actually is happening? See here on this chart, on the top chart, you see our neighborhood. So on the left, you see the sun, our planet, solar system, all the planets of the solar system. And on the right, you see our stellar neighbor, the Alpha Centauri system. And because this chart is given in logarithmic scale, so you see conveniently in the middle of the chart, you see a solar gravitational lens and the focus of the solar gravitational lens. Let me talk about how the optics of that solar gravity lens is actually represent itself. If on the bottom of that chart, you see a plane wavefront infalling onto the sun, and depending on the impact parameter, different parts of that wavefront will be moving towards the towards the focal line or optical axis of that lens. So essentially, optical axis is the point, is the line connecting the center of the target, the center of the sun, and extending beyond that, beyond the sun on the opposite side from the target. And because the light cannot get through the sun, because the sun is so opaque for that, I mean, the light doesn't get through the sun. So unless we use neutrinos, and Nick and I, we have discussed using the solar gravity lens to study neutrinos, because neutrinos can go through the sun and their focus will be much closer at roughly 39 astronomical units within the solar system. And so if we're using light, we have to actually compute the light deflection based on the shortest impact parameter, which is the solar radius, the solar radius. And so because of that, the first point where the two light rays will intersect is at the distance of roughly 547 astronomical units away from the sun. It's a large distance. And so if that distance would be much closer, I believe we would be able to access that region much sooner. And so that's the main complexity, how to get to that point. And because light deflection is inversely proportional to impact parameter, so that the light ray that has a larger impact parameter will be focusing further away from the sun, forming something called focal line instead of focal point. So if you put a telescope, let's say 1 meter telescope, within the strong interference region around that focal line, potentially you can get that significant light amplification, which I discussed, which is 10 to the 11, well, essentially 10 to the 9th. 1 meter telescope will have a light amplification of roughly 10 to the 9th. And so the image that we have to sample, if we take our Earth if you take our Earth, which has a diameter of roughly 13,000 kilometers, and you put that Earth at 100 light years away, so the image of that object will be a cylinder with a diameter of roughly 1.3 kilometers. So now, once we position our spacecraft within this image cylinder and move within this image cylinder, we can sample that image with the sort of the diameter of that 1.3 kilometers. If you move spacecraft within that cylinder, we can sample the image and actually reconstruct the image. Our latest analysis suggests that 1 meter telescope can be used to get the multi-pixel image of exoplanet, which is situated, let's say, 100 light years away. Roughly, we can get images of 250 pixels. And we can do that within 1 year of integration time. And so on the background of the solar corona and all of the interesting features that solar gravity lens represents. So to do that, we need to have a telescope within modest aperture, and I'm talking about 1 meter just for the sake of argument. So 1 meter telescope with a coronagraph. And potentially on the right, you see the image that will be formed on the image plane of on the imaging telescope with the coronagraph. So you see Einstein ring will be shining on top of the solar corona, essentially. And with that, you will be able to move your spacecraft and collect the light to really reconstruct the image. So that's in principle. The challenge, of course, how to get there. We know that Voyager spacecraft, which was launched in 1972, now travels at the distance of 150 astronomical units away. And so that was done with the technologies that were available back in 1960s. Today, we can use other technologies that actually will allow us to fly there much faster and get very significant autonomy on board. So we have never done this before, but with the technologies that we already have, we understand that most of those technologies needed to get to this region are either already on the very high technology readiness level or can be developed to reach the reasonable readiness within the next decade. And so we are relying on solar sailing. Solar sailing is a technology that allows us to use, again, the sun for the other purpose, because solar radiation pressure will be useful here. Once you open the solar sail, essentially solar sailing materials are available now to get to close proximity to the sun, to the distances of roughly 15 to 20 solar radii. Once you open the sail, you can fully benefit from the solar radiation pressure, where photons that are part of the solar process essentially will transfer momentum towards your sail, and you will be able to reach velocities of roughly 20 to 25 astronomical units per year. So just to put this in context, New Horizons is the spacecraft that currently holds the record of being the fastest. New Horizons was traveling at the speed of roughly about 3 astronomical units per year, with velocity of 15 kilometers a second. So with the solar sailing, we can improve that record by a very significant number. So we are aiming at developing technologies and demonstrating them, essentially that will enable us to fly at the speed of roughly 20 to 25 AU per year. So that's basically the general concept. Let's go a little bit into the discussion how it all works. So this is on the right, you see on the bottom, you see the point spread function that solar gravity lens has. On the top, you see exactly the functional form of that PSF, essentially. And the ratio R sub G is the Schwarzschild radius of the sun, which is about 3 kilometers. Lambda is the wavelength which we use to observe. And basically putting all the numerical values together, you see the number of 10 to the 11th. And so when you average it over the telescope that you use, like 1 meter telescope, you get it down to roughly 10 to the 9th. But so solar gravity lens give us 3 major advantages. It has a very significant brightness amplification, as I mentioned, 10 to the 11th. It also has a very nice angular resolution. Remember, angular resolution is given by the ratio of lambda to the diameter of your telescope. In this case, our telescope or our lens essentially is the diameter of the sun. So lambda over d gives you roughly 0.5 nanorec angular resolution, which is extremely difficult to get with the current technologies, because the current telescopes can be built to provide resolution of roughly 10, maybe 10 microseconds. And you need to have very significant efforts to get there. But technology exists to get us to the tenths of microseconds. To get to nanosecond, there is no technology. We don't know how to build it yet because it's very difficult. Solar gravity lens has that capability. The native diffraction limit with the solar gravity lens is 0.5 nanoseconds. And again, I just emphasize that the image is formed in the strong interference region of the solar gravity lens, where where sort of extremely narrow pencil sharp beam, where the whole image is now focused to the diameter of roughly 1.3 kilometers. And so the objects that are closer to us, for example, at 10 astronomical units, the image will be now slightly larger. It will be 13 kilometers. So essentially, we need to position our spacecraft within that the image cylinder, and that will allow us to actually do this the imaging of using the solar gravity lens. So moving on, our simulations show that the optical properties of the solar gravity lens significantly affect the image reconstruction process, because the lens has a significant spherical aberration. It doesn't have a focal point; it has a focal line, and because of that, the focal line actually leads to spherical aberration. Because of the spherical aberration, we have a significant blurring of the image. So on the left plot, here on the left chart, you see the original black and white image of our planet. Then in the middle, we see that image convolved with the point spread function of the solar gravity lens. So you see the blurriness, how blurred the image is. This is because of the properties of the solar gravity lens. But still, you can still recognize some continents within this blurry image. And if you do deconvolution, sort of image reconstruction with the reasonable approach, without sort of just using matrix inversion, you get image reconstructed on the right. So on the right column is image reconstructed. And originally we thought that there will be chromatic aberrations, but if you use this solely a monopole lens, sort of not taking into account quadrupole contribution from the solar gravity field, so the chromatic contributions do not come, and essentially we can talk about essentially reconstructing images of the color images. So using the solar gravity lens, which is modeled as a monopole, so gravitational monopole, you can see that potentially we can taking the color image of our own planet and convolving it with the point spread function of the SGL, you get a very blurry image of our own planet, as it will be sampled by the telescope in the focal region of the solar gravity lens. And you see, you can still sort of identify continents. You can see some, California is there. You can see United States. You see, sort of the weather pattern, and but then when you do a deconvolution, the image is beautifully reconstructed, and you can actually recover image without a significant impact on the quality. Of course, the higher the resolution we want, the longer the integration time we need to have. So this image, the black and white image with 128 by 128 pixels, can be reconstructed within 1 year of integration time. And this 1000 by 1000 pixel image, we need quite a bit of longer. So potentially 500 by 500 image of our Earth at 100 light years away can be done within 5 years of integration time. It's still a realistic mission lifetime. But if that uses assumption that we use only one telescope. If we use several small telescopes launched there with solar sailing capabilities, and those telescopes the number of those telescopes will actually, the larger the number, the more sort of the shorter time integration time it will require. So this is the capability, optical properties of the SGL. Potentially, we can remove the blurriness, remove this spherical aberration that is inherited in the solar gravity lens, and removing it, essentially we can that can lead to very nice quality imaging. So let's talk about the summary of our efforts that we were able to demonstrate during our NIAC phase 2. We understand that the solar gravity lens perhaps is the only way to see, confirm, and study exolife, because we can do direct imaging of exoplanets. All the other techniques they call direct imaging. It's not quite that. They can see the presence of exoplanets orbiting their host stars. So there will be some gaps in the exozodiacal cloud around the star, and so they will be able to identify those gaps. But they will not be able to see exoplanets directly. Solar gravity lens puts this conversation in a very different domain. So now we can talk about multi-pixel imaging of exoplanets. So potentially we also did, in addition to that, we were able to design an affordable mission architecture, which is using now revolution that is ongoing revolution in the small spacecraft design, because we can use ride-share opportunities using small sats with the solar sailing architecture, and essentially deploy those spacecraft in a very fast trajectories. That those trajectories will enable us to get to the solar gravity lens region within roughly 20 to 25 years, which is quite nice. And so it still can be done within the lifetime of a scientist. So our objective is, of course, so that once we launch the mission, we will be able to see the images. And the strategy that we put together, essentially within our NIAC phase 3 study, within the next couple of years, we'll have to develop a technology demonstration. Critical technologies need to be demonstrated. One technology is, of course, we need to fly a solar sailing spacecraft around the sun and show that we can reach not only the high velocity that is offered by the solar propulsion, but also pointing, high precision pointing. We can target asteroid, we can target maybe interstellar objects with the solar sailing. And those solar sailing spacecraft will enable us to go outside the ecliptic plane, which is currently impossible or very difficult to achieve with the chemical propulsion. So we have a very interesting spacecraft design. I will show you in the next few charts. And we are building now something called technology demonstration mission. Technology demonstration mission will allow us to demonstrate multiple of those technologies that we hope to fund using public-private partnership, where we are working now with the private sector, bringing multiple private companies into the mix and trying to see what those companies need for them to join our effort here. And so we are looking at building those maybe series of TDMs, inexpensive, less than $20 million per mission, flying them and showing the critical capabilities. Ultimately, we hope to fly the mission somewhere in 2030s, and the image of exoplanet maybe to confirm in life on another planet, hopefully to get some time by 2060. So this is the good motivation to live longer and stay healthy. So despite the pandemic, we need to do this. But now let's talk a little bit about sort of optics and the technologies that we are developing. So first of all, a little bit how we make the imaging of extended sources. So this is our sun. This is the image plane, not image cylinder, but image plane. And essentially each image, position of the telescope. Here we have a telescope positioned in the image plane. It immediately points to a directly imaged region on the exoplanet surface. So this is our source. And so this region is directly imaged. But because of the blur, our telescope here in the image plane also collects light from the rest of the exoplanet. So the blur contributes a lot of other signal into the telescope. And essentially this is a good thing, because our telescopes, a 1 meter telescope isolates a directly imaged region, which is roughly 20 by 20 kilometers on the exoplanet, which is situated 100 light years away. And so it's the light from that region is rather dim, but combination of the entire light from the exoplanet at a different proportion that comes into the telescope enables a very significant flux from the telescope. So essentially, this is a part where the blur comes in. We get a lot of flux, a significant photon flux, but also we have this impact of the spherical aberration. I'll talk about this, how we can actually use that to remove that aberration. So if we take a telescope, optical telescope with a simple convex lens, when the telescope is positioned in the image plane, on the sensor sees the Einstein ring. So imaging telescope right away sees the Einstein ring around the sun. On the left, you see the wavefront that is now light, which is passed by the sun. So light that has solar corona, has lots of other noise sources. We can put coronagraph in this instrument. Here coronagraph to block the solar light. But now in the image plane of that simple telescope, simple-minded telescope, you will see a sensor will see the Einstein ring. So potentially, if we see the light from the directly imaged region, remember we discussed the directly imaged region right here. So the telescope will see a faint Einstein ring from the directly imaged region, but a very bright light coming from the rest of the exoplanet. And so a combination of these two signals from the directly imaged region and from the rest of the exoplanet, this is what our telescope actually sees. And so moving on, if we compute the fluxes, the expected signal flux from different targets. Here on this chart, what we see is the flux which we will be able to see within the 1 meter telescope at 1.3 parsec away, the closest target, the Proxima b. We're talking about roughly 10 to the 7th photons a second within 1 meter telescope. The target at 30 parsec away, when we are able to compute the fluxes, which is roughly 10 to the 5th photons a second. And so if there are no solar corona, so detection sensitivity is incredible. So essentially, if no solar corona, we're talking about 2000 as signal to noise ratio in 1 second. So but this would be nice, but it's not the real picture, because we need to deal with the solar corona, of course. And so, but if you don't include solar corona in the picture, just to see how things are done, again, on the left, you see the original image. On the right, you see convolved image, and the blur is evident now. You now you understand where the blur is coming from. It's basically a spherical aberration that solar gravity lens has. But removing that blur is not a major problem. It can be done with the simple matrix inversion and a little bit cleaning of the cleaning technique. So basically, that's actually this can be done. So moving on, we need to take into account the solar corona, of course. Solar corona is very bright, it's turbulent, it's variable, and the impact of the solar corona is quite interesting. So if I take just the shadow, looking at the incident plane wave, and the plane wave impacts on the spherical object that has no gravity and no plasma. So the shadow, if you're not talking about Arago spot here, the shadow will be just cylinder extending to very large distances. If we take now plasma, so here on the right chart you see plasma. Plasma actually bends the light outwards, not inwards, but outwards. And you see that because of the negative refraction index, which is characterizing the properties of the solar plasma, you see that the solar plasma actually bends the wavefronts outwards, and you see how it's shown on this chart. But gravity works in opposite direction. So gravity bends the light inwards, and see how how the wavefronts are bent here. So they're bending inwards and forming caustic in the focal region of the solar gravity lens. When we combine two of them, so the gravity bend inwards and the plasma bends the light outwards. And so for certain frequencies, like we're talking about microwave frequencies like 3 centimeter, 10 centimeter wavelengths, pretty much gravity and plasma compensate each other. And so there is no lens essentially for those wavelengths. But if you're talking about optical wavelengths, where the wavelength of, let's say, 110 micron, maybe 0.5 micron, pretty much the effect of plasma is negligible, can be completely removed, and it's not affecting the light sort of bending properties. So this is why solar gravity lens makes sense for the optical properties, but not for microwave frequencies. Moving on, now imagine yourself sitting on the spacecraft that is moving at a very large distance from the sun at the focal region. So essentially, when we're looking at the sun is very bright. And when we positioned at 600 astronomical units away from the sun, this is the environment that our telescope sees. So this is electron density, which light, when it travels through that, it's so on the left, you see the solar diameter, so solar radius. When we move at 600 astronomical units, it's roughly 1.2 solar radii here. So this is the distance 1.2 solar radii. We still in very strong electron density regime, and the brightness of the solar corona is quite bright. It's quite bright here. When you move to 1500 astronomical units, it decreases by a factor of about 100. So, but for our mission, we're aiming at this region where we need to be able to operate at reasonably bright solar corona brightness. And so our coronagraph need to be able to block the sun to the level of solar corona, because we still need to have, we need to block the sun, the solar contribution, but we still need to have the Einstein ring to be observed by our telescope. So essentially the signal from Einstein ring will come with the signal from solar corona. So solar corona is a strong background on which we have to observe. And this is the sort of the reality we have to deal with. Our instrument will be significantly affected by the background from the solar corona. And so this is how the if you look at the sun, when the sun has no corona, you see the dark spot here, the dark area, and this is the Einstein ring. It's a very thin line around the sun. So now, of course, the sun is bright and the solar corona is there. You see bright light from the solar disk, and you see a solar corona which is everywhere. And so sort of this square area is our focal plane of our imaging telescope. In reality, of course, if we don't do anything with the sun, our signal is buried in this noise. So we need to block the sun, and this is what is achieved by the coronagraph. We have a coronographic design that allows us to block the sun, but still solar corona still shines through. What we can do with the techniques that we used in coronagraph design, essentially, this is our resolution element of our telescope. And so essentially what with the 1 meter telescope, Einstein ring thickness is not resolved, but Einstein ring circumference is resolved by 16 resolution elements. So essentially we definitely see the entire Einstein ring circumference, but not the thickness of it. So essentially this is the disk where we'll get the whole light, not only Einstein ring, but also the solar corona. And so our objective is essentially block all that region, essentially forming, essentially reading only the light that comes from that disk. And so this is our coronagraph that we designed to achieve that type of measurement. And putting things together, let me just maybe jump a little bit faster here. So essentially, as we move further, solar corona is rather bright. So these are the signals from our telescope, from our exoplanets. And as we discussed, the closest planet near us is Alpha Centauri, and the Proxima b here at 1.3 parsec away. The furthest planet that we discuss here is 30 parsec. Solar corona is overshining this signals. So, but integrating longer, essentially, we are able to get the sensitivity back, and so to recover sensitivity. And so we are able to get roughly signal to noise ratio of 10 to 20 within a reasonable integration time. And so that's how the signal to noise ratio is affected. So it's surprisingly, but signal to noise ratio improves with distance because we sample less corona, and essentially our sensitivity improves. If you're talking about exoplanet at 1.3 parsec away, in pretty much starting from 600 astronomical units away, our sensitivity is as we get an SNR of roughly 50, and the SNR of in 1 second, SNR of for a distant planet, we're talking about roughly SNR of 10. So which implies that we already we need to integrate at every pixel pretty much few seconds. Within 10 seconds, we get enough light to actually overcome the impact of the solar corona. And so with that, integrating longer, we just built a much better data set with a very good sensitivity. And so if we integrate for 1 year only, a number of pixels that we will be able to achieve for exoplanet at 1.3 parsec away, and the distance of roughly like 650 astronomical units, for that planet, we can get 250 by 250 pixels across for that closest exoplanet. For the furthest exoplanet, let's say 30 parsec away, we can get roughly 70 by 70 pixels with 1 year. But if we integrate longer, let's say mission getting there 25 years of flight and operating there, we should be thinking that we can operate for at least for 10 years. And so within 10 years, our number of pixels that we will be able to get from that exoplanet is really improving. And if I may remind you, if I want to get 100 pixels images for an exo-Earth at 10 parsec away, the telescope diameter, if I use classical telescope, must be 3,000 kilometers. So just to put this in perspective, if I want to achieve the same sensitivity with classical telescopes, I have to have access to a telescope whose diameter is 3,000 kilometers, which is pretty much, I mean, that's again, the point is solar gravity lens is challenging. I'm not saying that's easy. Lots of things will be complicated, but it seemed to offer us a very interesting way out, and that will provide us not only with imaging capability, but also with spectroscopy of exoplanets within sort of realistic lifetime, within maybe next couple of decades, if you do that. And so these are the images that we can develop. This is what we're aiming for. So moving on, technologies. I will briefly jump through the technology slides here just to give you the flavor. We went through multiple technologies and we understood the propulsion is very critical technology to have. Chemical propulsion, present-day chemical propulsion. For that, we need to get, first of all, chemical propulsion by itself is very difficult. Again, New Horizons was launched on Atlas rocket and essentially reached the highest velocity possible with chemical propulsion. To further improve that velocity, we need to form a trajectory going towards the Jupiter, towards Jupiter, then to perform a gravitational maneuver, and then fall into the sun. Flying by the sun at a very close proximity, then we can fire a solid rocket motors, and then that will allow us to get a very large velocity of roughly 15 astronomical units per year. For that, we need to make sure that the spacecraft will survive the solar proximity, and so it's kind of challenging, but the limits are here quite significant. We're talking about 15 AU per year, which is quite a slow velocity compared to what we need. Solar thermal, 22 AU per year, nuclear electric, and solar electric sail. Those technologies are very low technology readiness level. Chemical propulsion is flying today, but solar thermal, nuclear electric sail, they're being discussed, they're being developed, but their readiness roughly maybe TRL 2, TRL 4 at most. So they're not there that we can benefit and work with them in the near future. So this is why we went to the technologies that is solar sailing. This is the solar sails that were flown recently. Icarus is a Japanese mission. Then Light Sail 2 was launched on Falcon Heavy, developed by the Planetary Society. And essentially, Near Scout is being developed now in the Marshall Space Flight Center. And so NanoSail D is another technology that in another spacecraft that was able to that demonstrated capabilities of solar sailing. So with this, we understood also that the planar sails have limited capabilities because they're unstable, and we decided not to go with planar sails, and instead we use a vane technology to be able to articulate vanes. And essentially here on the left, you see the spacecraft vanes that was developed by Lagarde, company Lagarde, Sun Vane in 2010. Today we are developing a different technology, sort of it's Explore Incorporated, the company that is developing solar sailing spacecraft with vanes that can be articulated using shaped materials. And so here you can actually tuck into the sun like a sailboat against wind. So by articulating vanes, you can lose your angular momentum, which you have launching from Earth, and then you can fall into the sun. And what I'm showing here is that we can actually reach from the solar, from Earth or from high Earth orbit, reach solar perihelion in 3 months by tucking into the sun. And then when we're flying by the sun, we can reach velocities at far faster than 5 to 7 astronomical units per year with technologies and the sail materials currently available. And so this is why to get to the solar gravity lens area, we're using solar sails, because this is the technology seem to offer a lot of advantages for what we need, because it's a technology that can provide us with a very fast transit through the solar system, moving it at any inclination, because chemical technology, it's possible to use 15 AU per year with some constraints, but very difficult to do this with targets outside the ecliptic plane. Here we're talking about unconstrained target access with solar sails. And so maybe here, just in the sort of the grand vision here, not going into details, we will now launch multiple small spacecraft. Each of them will be maybe 50 to 100 kilograms. Once those spacecraft launch, they will be assembled and they will unfold their sails and will start moving towards the sun, tucking into the sun. Once they actually passing by the sun, they will be already moving at a very fast velocity, very high velocity. With the high velocity, moving somewhere nearby the orbit of Mars or approaching Jupiter, we don't need sails anymore. We can drop those sails. And essentially those spacecraft can now be brought close to each other, and they can form a larger aperture, like a Lego style. So essentially in-flight assembly can allow us to build a larger aperture telescopes, not 30 centimeters that is possible now with small sats, but we're talking about meter class telescope, which will assembled in flight. And then using those telescopes, moving on already very fast velocities, getting to the solar gravity lens focal region. And then after 20 years, we'll be getting to the 20-25 years, we'll be getting to the focal solar gravity lens focal region, where the light from the parent star, which will be also amplified by the solar gravity lens, will provide us a beacon. We'll use that beacon to actually acquire the signal for the parent star, and then we'll start looking for the planet orbiting that parent star, moving away roughly 100,000 kilometers away in the image plane using ion propulsion. And so this is rather easy to accomplish. And so getting there, we'll be able to actually move with that target along its trajectory around the planet, around the star, and being able to actually get the signal, enough signal to noise ratio to reconstruct the image. So this is my, I guess this is my last slide. With the very good knowledge of the optical properties of the solar gravity lens, we can now confirm that the solar gravity lens can be used for imaging of very faint objects, such as exoplanets. Additional layer of knowledge comes from our ongoing work to incorporate multiples, solar gravity lens, not only monopole, but quadrupole, octupole, and other multiples. They will complicate analysis, but actually our work now suggests that even with those inclusions, the mission is still feasible, and we can reach a very good resolution within realistic mission lifetimes. So we now fully account for the solar corona. We now fully account for the multiple structure of the solar gravity. And what is yet to be counted is temporal variability of the planet is rotating. And so the weather is changing, weather pattern is changing. And our sun is not fixed to a space because it's being pulled around by Jupiter and Saturn. So the trajectory design that we have now can account for this type of predictable motion. What is left is temporal variability when the planet rotates and when it moves around the host star. That yet to be accounted for, and we need to show how we can actually overcome those challenges, because we need to understand that getting a spatial resolution, we can do that. Now we need to improve temporal resolution. So the temporal resolution will allow us to remove cloud cover and get under the clouds and actually see the planet in full glory. We have interesting technology, and stay tuned, because during the 2 years of phase 3 study, we will be now looking at the ability to demonstrate critical technologies that are needed to fly that mission within, let's say, maybe a decade or two from now. So with this, thank you very much. And if you have any questions, I will be more than happy to discuss them.
Thank you, Slava. That was very nicely done. We have time for questions, answers, and discussions. If anyone in the audience wants to ask anything, just unmute yourself and speak up, or raise your hand. I'll call on you. It's up to you how you want to do it. There might be some comments in the chat. I see there's a box in the chat already.
This is the public materials that are available, which you would appreciate. There are some YouTube videos that were made to demonstrate the concept. and it's quite nice. Look at them and you see how technology is being deployed, because here in 1 hour, I jumped through many topics. And if you want to go deep into those, please look at those, papers. Don't go into technical literature, because technical literature, we're talking about diffraction of light in the solar gravity lens in the presence of the corona and how you do the imaging. But maybe you would like to get into the technical issues, and then we can form a collaboration. Actually, there are lots of interesting work to be done on the optics and how we actually build things to enable chronograph design, trajectory design, how to enable image reconstruction, and to remove all the artifacts that the lens has. And so if you're interested to work to collaborate on those topics, we'll be more than happy to discuss with you.
All right, if nobody else goes,
Well, there's a question from Dustin. He has his hand up. It's blue hand.
oh, okay.
Dustin, you want to go first?
Yeah, sure. I have a couple of questions. Did we think about how the spacecraft will slow down once we get out there?
That's a wonderful question, but because the solar gravity lens doesn't have a focal point, it has a focal line. We don't have to slow down. We just continue along that focal line and collect light as long as the mission spacecraft is healthy and so able to communicate.
The next question is related to pictures of other exoplanets. Are we able to use the same array of telescopes to redirect and point at other exoplanets? And
Dustin, another wonderful question. And with the current technologies, we are not able to redirect. Once we'll have, like, let's say, technologies relevant, maybe nuclear fission or some other, abundant power on board, then not a problem. Now, I look at this mission as a typical planetary mission. When we fly towards Saturn or Jupiter, these planets have a lot of satellites. So once we get to Jupiter, we study Jovian system. And so our spacecraft, Galileo or Cassini around Saturn, were flying around those planets and studied all those satellites. Same thing here with TRAPPIST, for example. We can see every single planet orbiting that star. So it's a single system, single planetary system mission. So, but to redirect it, we are not talking about redirection because technologies that we have do not allow us to do that. But with the cost that we hope to derive, if we are now develop everything trying to save cost, because during the phase 3, we'll be looking at the cost of that mission, of course. We'll be looking how much can we reduce into incorporating new technologies. So the hope that the mission will be affordable, and with the public-private partnership that we are aiming to build, we hope that the cost can be shared. And if the cost of that mission is comparable to the current cost of missions, we're not talking about 10 times or 100 times more expensive, but if the cost is really within the scope of current missions, so then maybe we can fly several of those missions to the most promising targets. So it's you see, this conversation is yet to be yet to have, because we need to integrate a lot of new technologies. Current missions require a lot of time to communication as a bottleneck. And so basically you have a fixed cost in developing spacecraft, then you launch it. And so now the cost of operating mission, the team, communication, data analysis, this is what eats your budgets. But the fixed cost is essentially a launch vehicle, and the fixed cost of spacecraft design is already part of that. It's thrown away. And basically for many missions, the longer the mission operates, the more it requires cost to support the science team. As you know, for example, we were building multiple spacecraft that would be the requirement would be to operate 3 months. But after 10 years of operating, this spacecraft still operating, and the cost for that now, the sunk cost already there. So that we built the spacecraft. But now, so here we will rely in solar gravity lens, we'll rely on autonomy quite a bit. So we need to really integrate the capabilities so that the mission, we don't need to communicate with the spacecraft daily. We need to rely on its smarts so that we'll be able to fly, identify, orient, and alert us if there is some anomaly going on the spacecraft. But it must be able to resolve that anomaly, to address that autonomously. So we are cutting the umbilical cord for the spacecraft that we have, because currently the umbilical is connection link, communication link between the spacecraft orbiting somewhere around Earth, around the planets in the solar system, and the group of scientists and mission navigators sitting on JPL or Goddard or other center. So delegating more authority to the spacecraft, essentially we hope to save a lot of money and so the mission cost. That's the main idea. But we definitely need to rely on modern technologies that are being developed now, miniaturization of spacecraft, communication capabilities. And essentially, I'm not using the word artificial intelligence, but really it's kind of adaptive learning and trying to develop the idea, the algorithms that will preserve the life and sort of the health of the spacecraft and enable the spacecraft to recover from any failures or any anomalies it may encounter.
Thank you.
Okay, let's see. Holger had a question, I recall.
Yeah, first you mentioned the cylinder of the not focal point but focal cylinder at 20 astronomical units. How long are you going to stay in that cylinder? You mentioned also 10 seconds for a good signal to noise on 1 pixel. So how? I guess I wasn't able to put all the numbers together in my head quickly.
In our mission design, we expect to be within the cylinder for the entire mission duration. So until we are healthy, we must be within this 1.3 kilometer cylinder. And if the object is closer, so then let's say 10 parsec, or 10 light years. So that cylinder is 13 kilometers diameter. So we must be within that cylinder. And so as long as, if we image one single planet, and so then the mission duration, let's say, hopefully will survive in that region maybe 5 to 10 years. So that the entire mission duration, we should be able to benefit. The longer we observe, the more data we collect and more interesting features of that exoplanet we'll be able to identify. It's not only imaging, but now potentially spectroscopy and image and sort of the polarimetry. And we can study a spatially resolved spectroscopy. So think about not only global spectroscopy, but really you can identify spectroscopic signatures from an object somewhere on the surface of that exoplanet. So the more we integrate the signal, we will be able to build more of the spectral resolution as well.
The other thing, what about the host star of the exoplanet?
The host star is always there. And the host star, because it is amplified, so the light from the host star will be there, but to a very small level, because the point spread function of the solar gravity lens goes not like a classical PSF, like 1 over r to the third. It's like 1 over r. It still will be there, but will provide a sort of a constant background, similar to a little bit dimmer than the solar corona. So both of those signals will be there, corona and the host star. And the host star, I mean, if you look at the system, if you look at the host star, and around that host star the planet is orbiting, there will be some parts of the orbit where we cannot observe that exoplanet because it will be moving just in front of the host star. So we have to repoint our sort of observation to another object within the system. So if the system is edge on, not face on, but edge on, there will be part of the planetary orbit, let's say maybe 4 months on one edge and 4 months on the other edge, where we can observe. But we definitely will not be able to observe when it's within this, between the two periods, because actually the background will be very, very, very high. So we need to plan ahead and make sure that we know exactly what to do and when this can be done. Just wait longer and look at the different objects within the planetary system. So that's the idea. So potentially, if we have several planets in that system, we can just repoint the telescope to observe the next planet and just use that time wisely and to benefit, research of the whole system.
All right.
I think there's at least one other question, but maybe the person can ask their question themselves.
I guess you can read and we can talk about it.
Yes, hello. This is Terry Chappis. I have a question regarding. First of all, thank you for this presentation. Very informative. Great presentation. My question is, how would these clusters control? How would the control navigation guidance be controlled? How would that be handled going out
This
to
is
that focal
wonderful. The navigation is quite interesting. So getting there, we will rely on optical astrometry significantly because we are flying a light bucket with very good imaging capabilities. So essentially, when we look back at the sun, we will have, we will be, when you buy a new telescope, they tell you don't put it, don't stare at the sun. So we do completely opposite. We will have to have a telescope that will look exactly at the sun. And so we will be able to see the edge of the sun, and we will be able to see maybe a couple small spacecraft with laser beacons orbiting the sun at 1 AU. And so those laser beacons will be used as a guidance signal for us to identify where our planet, where our Earth is, and what is the inclination of our spacecraft. So potential optical astrometry can be used. We can to navigate the spacecraft, but we don't need to have absolute positioning to very high level. We need to have relative positioning to a very, very reasonable level. And that is, if I have one single spacecraft, and that spacecraft, I track its position all the time, and then in the global processing, the initial position, it will be just a sort of a salt 4 parameter. So that's if I track each consecutive step, consecutive position of the spacecraft, solving for the initial position will be just part of the global data feed. And so this is one way if you're using one spacecraft. If you're using several spacecraft in that image plane, each of them, presence of additional spacecraft will essentially reduce the differential navigational precision requirement. And the other techniques can be used with quasars, X-ray navigation, lots of other things, but I'm not inclined to talk about those because they're prone to some, some systematic errors. And so we try to rely as much as possible on optical astrometry for that purpose. And so that is something that we will be able to position the spacecraft within a kilometer of the target, maybe a couple of kilometers of the target. And then that will allow us to really stay within the system by looking back at the maybe beacon spacecraft in the inner part of the solar system, or maybe the beacon from the Earth, because we do have high power lasers that will be used for, let's say, lunar laser engine, maybe direct energy transfer to the lunar base. Things like that will be deployed soon, and we can use something like that as a beacon. But it doesn't represent a major challenge. It will definitely require an engineering solution that we are looking for to develop, but it doesn't represent a major problem here.
Great, thank you.
Okay, any other questions before we end? I do have a few announcements. We had a problem with the speaker who's next week. She's from London, and she won't be able to make it because she has some family problems. And it's actually too short a notice to get a substitute speaker. So we'll just skip next week's seminar and then come back in 2 weeks. Okay, and let's see, again, would like to thank everyone for attending. The physics seminar series is funded by a gift from April and Eddie Lucas. We greatly appreciate their help, and we'll hopefully continue this for many more semesters to come. So thank you, everyone. Bye.
Excellent. Thank you.
Thanks, Slava. Came out great.
Excellent. Thank you.
Thank you.